Okay, so let's go through an example here of how to do a Rankine cycle. Okay. So the first thing that I want to do here is I want to kind of draw up the cycle. This is just like what we did before. So I got the boiler. It goes into the turbine. The turbine goes into the condenser. The condenser goes into the pump, and the pump goes into the boiler. And I'm going to use the same numbering system, 1, 2, 3, 4. Okay, so there's our basic Rankine cycle. The whole point is to get work out here. Unfortunately, I have to put work into the pump. There is heat that goes into the system from the boiler, and I reject heat to the condenser. We heat out. Okay, so that's everything there. That's the same thing. There's nothing new here. Everything's the same. Okay, so now what we need to do is we need to read this problem and figure out what we need, what it's asking. Okay, so we've got an ideal Rankine cycle, and it has a net power output of 45 megawatts. Okay, so what do you think that means when it has a net power output of 45? What do you think that practically means when I say that, 45 megawatts? Yeah, it means the work out of the system minus the work in, okay? And of course the work in is the pump. Okay, so we got that. Steam enters the turbine at 7 megapascals, 500 degrees Celsius. So that's the temperature and pressure of what state? 1, 2, 3, or 4? 3, right? Yeah, 3, yeah, right? Because 3 is what's going in the turbine. So what we're saying here is that on each one of these things, state 1, state 2, state 3, and state 4, okay, I need to figure out some stuff on each state. And I definitely know the temperature at state 3 is 500 degrees C. Got it? All right? And I know the pressure at state 3 is 7 megapascals. Okay. Good. What else do we know about some of these states, given what I defined about the Rankine cycle? Can anybody, do we know anything about 1, 2, or 4? I'm thinking we must know some other things, right? P2 is equal to P3, that the pressure going into the boiler is the same as the pressure coming out of the boiler because it's a constant pressure process, yes. So P2 is also equal to 7 megapascals. Good. Okay, what else do we know? S3 is equal to S4, so good. So I know S3 equals S4, that's good. Anything else? P4 and P1. And by the way, what is that pressure? Read the problem. What does it say? 10 kilopascals. It says, if you read the problem, it says it's cooled in the condenser at a pressure of 10 kilopascals. Okay? So that says here P4 is 10 kPa. Is that a low pressure? Yeah. In fact, it's lower than atmospheric. It's like a vacuum. It's like a vacuum. If you bust open those pipes in the condenser, it doesn't want to come out. Stuff wants to go in. All right? It's like a vacuum. Okay, and so P1, by the way, is also at 10 kilopascals. And S1 equals S2. That's right. We can definitely say that. Okay. Now, I'm going to tell you this. The key to doing these problems is to get your enthalpies, okay, to get your H's. Once you get the H's to every state, the rest of this thing goes pretty quick, okay? So what, state 1, 2, 3, or 4, what H would you like to get first? Anybody? Anybody want to get an H? And how are we going to get an H? Probably tables, right? At least somewhat. So any of you like to go first with? 3? Yeah, I got everything, right? I know 2 things about state 3. It's temperature and pressure. So I'm pretty darn sure I can look that up in my tables. So I go here, and I go to my tables here. Row tables, blah, blah, blah. Here we go. And I go to, let's see here. This is 3 is a temperature of 500 degrees Celsius and a pressure of 7 megapascals. I'm going to pretty much assume that's superheated because everything at 500 megapascals, 500 Celsius is superheated. So let's do that. Let's go here to water superheated. Superheated water at 7 megapascals. That's where we're at. And 500 degrees Celsius. Okay, there it is. My H, my enthalpy is 3411.4. So I'm going to write that down. 3411.4 for H3. Kilojoules per kilogram. Okay. I got my first one. I got my enthalpy at state 3. Yeah, where do you want to go? You want to go there? That sounds like a good bet to me. So let's go to state 4. We do know 2 things about state 4. We know its pressure of 10 kilopascals, and we know S3 equals S4, right? We know both those things, right? So looks like I'm going to have to go back to that same thing here. Look at S3. S3 is pretty much 6.8. 6.8000, right? So I'm going to write that down. Oops. Let's write that down here. Let's see here. S3 is 6.800. That's going to be kilojoules per kilogram K. All right. So now, how am I going to get how am I going to get like H4? Yes, you got to look it up. So we got S4. S4 happens to be that same number, 6.8, and P4 is 10 kPa. So the only way I know to go to 10 kPa is to go saturated water pressure table. That's the only place I know has 10 kPa. So here we are. We're basically on this line right there. If you take a look at that, is 6.8 going to be on this table? Well, you got to look at the entropies, right? You got to look at the entropies, and you notice that my low entropy is 0.649, and my high entropy is 8.1488. So I think 6.8 is going to be somewhere in between. So how am I going to get H3? What? Interpolate, but what do I need to calculate? What's that? Quality X. That's right. Yeah, get the quality here, use it to get the H there. Okay, and then you got it, right? We've done this before. It's not. This shouldn't be new. Okay, so what I'm going to do is I'm going to get the quality. Now, to save a little time, and since we've done this before, I'm going to do this kind of on the fly here. I'm going to say, okay, 6.8 minus my low value, which is 0.6492. Then I'm going to divide it by the evap term, 7.4996, and I get quality of 0.82. Okay? So it turns out if you do this right, you will get a quality for H here of 0.82. Okay, so if you have that quality, then you go back to the tables. You say, okay, I'm here. Now let's take a look at enthalpy. If you take a look at enthalpy for a quality of 0.82, you multiply that by the evap term, which is 2392.1, and then you add it to the sat liquid, 191.81, and you get 2153.7. We'll say that. So I'm going to write this down for you. You basically get H4 of 2153.7. 2153.7 kilojoules per kilogram. All right, that's good. We got those two. 4 was a little bit harder than 3. I had to get the quality, then I had to go back and do all that to get H4, but you know, that shouldn't be new to you. How am I going to get 1 or 2? Any thoughts on how to get H1? I got to get H1, enthalpy at state 1, and I got to get the enthalpy at state 2. Got to have all my H's, because I really can't do anything unless I know the energy of each state, and enthalpy represents that. What do I know about state 1? I know its pressure is 10 kilopascals. Is there anything else I know about state 1? Based upon the Rankine cycle and... yeah, but I don't know S2. I don't know S1. I don't know S2. Remember anything? What do I know about from Rankine? Basic Rankine cycle analysis. What comes out of a condenser? What comes out of a condenser? Stuff that's been condensed. What do we call that? Saturated liquid. Yeah. So we're going to assume 1 is pretty much sat liquid. Okay? We're going to say this is sat liquid at that pressure. Right? Well, that's easy then. Once you tell me it's saturated liquid and it's a pressure of 10 kPa, oh, I can do that. I can go back to my tables, right? Go back to my tables. Here I am. I'm on the table already. Saturated liquid, pressure 10 kPa. My enthalpy is right there, 191.81. Okay, that's easy. So it's 191.81 kilojoules per kilogram. All right, that's good. Now, last but not least, we've got to get state 2. Now, with a pump, we have an equation, okay? And this is where we're pretty much going to use this pump equation all the time, okay? And that is the work of a pump, I already gave this to you before, the work of the pump is equal to the specific volume of what you're pumping multiplied by the pressure difference. Okay? So in this case, I can easily calculate this pump work. What's the specific volume of the liquid going into the pump? Well, that's the same as the specific volume of saturated liquid at 10 kPa, right? So I go back to my tables and I go, what's sat liquid 10 kPa? What's its specific volume? Oh, it's right there. It's a very low number, right? It's 0.001010, right? So I go here and I say, okay, this is 0.001010, and those units, by the way, are meters cubed per kilogram. Okay? So that's the specific volume. Anytime you do a pump equation, and your number for specific volume is not really low like that, something's wrong. Because you're pumping something that's not low specific volume, that's not good. Okay, now what's the pressure difference? Well, what are we doing? There's only 2 pressures in a Rankine cycle, a low pressure and a high pressure. Yeah, the high pressure is 7 megapascals, right? The low pressure is 10 kilopascals. So let's use the same units. This would be 7,000 kilopascals minus the initial pressure, which is 10 kilopascals, right? So it's really 7,000 minus 10. Now you got to watch your units. This is going to be in kilopascals. If you multiply these two together, you basically get, and you'll have to confirm this on your own, kilojoules per kilogram. Okay, so this works out. If you do 7,000 minus 10, of course you get 6,990. You multiply that by 0.001010, you get 7.06 kilojoules per kilogram. So the work of the pump is 7.06 kilojoules per kilogram. So now, let's think about this for a second. Don't give me a number, just give me the concept. If I have so much energy going in, H1 is 191.8, and then I have the work of the pump, what's the energy coming out of the pump? Energy going in, work going in, what's the energy going out? Any thoughts? First law of thermodynamics, anybody? Well, now, this is easy. Don't overthink it. H2 is equal to what? The energy coming in plus, energy in equals energy out, right? So energy in is work of the pump plus H1. The energy out is H2, right? That's it. So H2 is equal to the energy going in plus the work of the pump. That's it. Just add the two numbers. So it's very small difference, you'll notice, right? You take the 7.06 and you add it to 191.81 and you get 198.87, I guess, whatever. Okay, kilojoules per kilogram. Now, we've got a little bit of time left to answer these questions. Let's go through some concepts here. What I want you to do, I want to see if I can do this. Okay, I can't exactly do it, but I know on your paper you can do this. You have all the H's and you have your little diagram, right? Tell me, you don't have to give me the exact number, just give me the concept here. Tell me what the work out is of the turbine. How much work does the turbine produce in kilojoules per kilogram? Anybody want to give me what that is? What's the work of the turbine out of the system in kilojoules per kilogram? You don't have to give me the exact number. Tell me what it is. You're making it more common. Yeah, you could do that. You could do it. I'm just saying, give me the work of the turbine. Oh, H4 minus what? H4 minus what? H4 minus H what? 3. Yeah, don't overcomplicate it. It's that easy. It's that easy. Yeah, don't make this harder than it needs to be. Yeah, the work of the turbine, okay, it's H3 minus H4 really, because that would be positive. But if you said H4 minus H3, no big deal, right? The work of the turbine is just the difference between the H's on both sides. Okay, you got that? So the work out that we get here, the work output, let me do this here, is simply H3 minus H4. Okay? Now, what about the pump work? How much is the pump work? Well, you already told me that. We already calculated, right? It's 7.06 kilojoules per kilogram, right? What's H3 minus H4? Well, we can calculate that. I'll do that real quick for you. H3 minus H4 is 3411.4 minus 2153.7. H3 minus H4 turns out to be 1257.7 kilojoules per kilogram. Cool. That tells me that I have to put in 7 kilojoules per kilogram of energy to make this all happen. But good news, I get 1,257 kilojoules per kilogram of energy out. Pretty cool. I get a lot more energy out than I get in. That's better, right? If that didn't work, we wouldn't have power. So I'm glad that works. Okay. What do you think is the network? What do you think is the net? Well, first of all, give me we already defined the network, didn't we? Didn't we say that the network was equal to the work out minus the work in? Okay. So let's do that for us. This is an easy number, right? What is the work out minus the work in here? What is it roughly? What's 1257 minus 7? 1250, right? I mean, roughly it's 1250. If you would like, we'll go through the actual number, and I'll subtract 7.06 to make you happy, and we'll get 1250.6 kilojoules per kilogram. Okay, that's my net work. Okay, that's my work net. Okay? Now, that is expressed in kilojoules per kilogram. But remember that the net work that I get in terms of power is a rate of energy. The net power is equal to 45 megawatts, right? By the way, that's also 45,000 kilowatts, right? All right, so what I have here is the first law of thermodynamics. Remember this one? Here, I'm gonna write it here in blue just to remind you. Remember this one? Q dot minus W dot is equal to M dot H2 minus H1. Now, if we just look at this, we can clearly see that basically what we have here, W dot, is equal to 45,000 kilowatts, is equal to the mass flow rate, which I don't know what it is, and this here is the net work. So this is going to be 45,000 kilowatts equals mass flow rate times the net work, which is 1250.6 kilojoules per kilogram. And then if you back solve this, which I will here, let's see here. You get a mass flow rate of the steam. This is mass flow rate steam inside the cycle of 35.98. Cool. Okay, we got that. Now we've got a couple more things, so hang with me. Give me a couple minutes, if you can, of your attention. We're almost done. Okay? Okay, here's another one. This is an easy one. What is the efficiency of the cycle? Efficiency is always what you get out divided by what I put in. What I get out is net work divided by what I put in is Q in. Right? Now, we've already solved for the net work of the cycle. In fact, we have it here. It's at the top of my thing here. It's 1250.6 kilojoules per kilogram, right? That was the net work of the cycle. Can somebody take a look at your diagram, don't overthink it, and tell me look at the boiler, right? That's where the Q in is. That's where the heat comes in. What do you think is the heat in from the boiler? Not change in temperature, change in energy, which we express as enthalpy, H, right? So the Q in this case, would be what H's? What H minus what H? H3 minus H2. Very good. That's how we do it. And so this is going to be 1250.6 kilojoules per kilogram divided by H3 minus H2, which we have to do here. Have to look these up. H3 is 3411.4. H2 is 198.87. And we get 3212. So this is going to be 3212.5 kilojoules per kilogram. So now I'm going to multiply that and figure this out. I get an efficiency of 0.389, about 39%. 39% thermal efficiency. So basically, if I burn all that coal or whatever it is, in this cycle, I get about 39% of it to useful energy. The other 61%, sorry, throwing it in the river. Throwing it in the lake, throwing it away. But at least I got 39%. Okay. The last step here, and this goes quick too. The temperature rise of the cooling water. Okay. We already calculated, no, we haven't calculated the Q out. We haven't calculated the wasted heat. Now, go back to the diagram here. Take a look at that picture. Tell me what is the heat that goes to the condenser in terms of my H's? Any guesses?
From 4 to 1.
H4 minus H1 maybe? Yeah, how about that? Yeah. H4 minus H1 is my Q out. Okay? Which, by the way, I can calculate pretty darn quick here. And that is going to be 2153.7 minus 191.8. It's going to be 1961.9. Okay, so this is 1961.9 kilojoules per kilogram. What's my total Q out, though? What would I have to multiply that by to get the total amount of heat out? Because that's in per kilogram. The mass flow, right? The mass flow, which I've already calculated. My total Q out is my m dot of the steam times that 1961.9. Okay, so I multiply that by my mass flow, which I have up there, 35.98, which I forgot to write as kilojoules per, kilograms per second here. Okay. And so I do that, and I get this. I get 70,589, okay, and that's going to have to be kilojoules per second, which is the same thing as, of course, kilowatts. Okay? So last but not least, all that Q out goes into the water. It goes into water that's flowing through. Okay? All that Q out goes into some water. So it says here the mass flow rate of the water is 2,000 kilograms per second, right? So how do you get the temperature rise? Yeah, specific heats. Specific heats. Here's how you do it real quick. You're going to say this. You're going to say that Q out is equal to the mass flow of the water times the specific heat of the water times the delta T of the water. So what you got here is 70,589 equals 2,000 kilograms per second. Remember, specific heat of water is 4.18 kilojoules per kilogram K. And this is delta T. And so it's a pretty quick calculation there. You've got to take that number, divide by 2,000. Shoot. You got to take that number and divide by 2,000. Okay, and then divide by 4.18, and I got 8.44. So the rise in temperature is about 8.44 degrees Celsius. The EPA is not going to be happy with that. They're not going to let you do that. But probably have to do better. But that's okay. That's your answer. All right.